All right, so this, we want to look into what we call Euler's method for approximating solutions of differential equations. Because keep in mind, although we've learned how to solve some differential equations, those are just very specific types, essentially those that can be, that are separable. There's many more types of differential equations. And so the idea, I guess, a visual understanding of Euler's method is if this is the actual true particular solution of a of a differential equation, we can approximate it if we know some point on the solution. We can approximate it with little linear segments of some step size, in which each time we create a new linear segment by finding out the slope of the differential equation at that point. And over time, especially with smaller and smaller step sizes, it tends to approximate the general solution. The more steps and the smaller the step size, the more it overall approximates and comes closer to the actual solution. So first, we need to review a bit with recursive equations. And this first question actually has nothing to do with differential equations, but ideally it gives you a sense to get a little bit of practice on your GDC, because we do have to be familiar with how to use the sequence features on your GDC, which is not something we've used before. And it's probably something you've never used before. So I have two recursive sequences here. X to the n plus 1 is the same as 2x to the n plus y to the n. And y to the n plus 1 is xn, yn. And then we're given some starting points. X naught is 1 and y naught is 2. So x starts at 1, y starts at 2. And so this is just about understanding how we read a recursive equation again, which goes way back to some of the first lessons in this course. So for part 1, I know what x naught is. X naught is 1. Well, x1 is the same as 2 times x n minus 1, or just, I should say n minus 1. This is, if this represents the term we're looking at now, this represents the term before it, which we know is 1. So this is 2 times 1 plus y, the previous term. So 2 times 1 plus 2, which is clearly 4. And I can do something similar for y1. If I look at y1, well, y1 is going to be the same as x0 times y0, the previous ones. And so y1 will be x0, which is 1, times y0, or y naught, which is 2. And so we get 2. All right, so now we know the x0 is 1, x1 is 4, y0 is 2, y1 is 2. I think we can just continue this. So I just want to do this one more time. So one more iteration of this. So now I can say, let's go with x. So x2 is going to be the same as 2 times x1. So in this case, 2 times 4 plus y1, which is 2. And so in this case, we get 10. And then y2 will be my previous x, so 4 times my previous y, which is 2. So 4 times 2, which is 8. And notice we could just continue this on and on and on. It's not difficult, it's just tedious and time-consuming, which, as always, are great uses of technology because they don't tend to get bored. And so for part 2, this is where you have to just on your own learn how to use the sequence features on your GDC. For example, in the TI-84, you have to change in your mode settings from graphing to a sequence settings, and it's in your y equals button, where you, instead of typing in an equation to graph, you type in sequences to sequence. And so when you do that for these equations, ideally first you'll see that these are correct, these values that we've got before. And then you should get, for x5, the 5th term, you should get, or I guess the 6th term, because we're starting at x naught, you should get 2,512. And y5, you should get 304,640. All right, so again, we want, as it says here in bold, it's really essential, it's imperative that you become clear with how you use your sequences features on your GDC. So assuming we have that down, now let's look at some questions that actually do apply to differential equations. So you have a fairly simple differential equation. It is a separable one. Dy dx equals just xy, and we're given some initial condition, y1 equals 0.5. So if we're to think about what we saw before, like graphs of these, like a slope field, we know that we can imagine this particular solution going through 1, 0.5. However, I want to see if we want to try using Euler's method. So first, without using anything in our GDC, let's use Euler's method with a step size of 0.5 to estimate y2. Well, first of all, what that means is if we're starting at y1 and we want to make our way to y2 with step size of 0.5, well, that means it's going to take us 2 steps to get from y1, which we know, to our approximation for y2. Essentially, it should be about the same amount of work as we did up here. That was 2 steps. And so first, we know that x naught equals 1. And how do we find our approximation for the next one? Well, in general, x of n plus 1. Every next step of your iteration is for x is going to start with your previous value for x plus the step size, which is just 0.5. And that's always going to be the case. Whatever the step size is telling us how often, how large our steps are for x. And that means, let me also let's look at y. So y naught, we know, starts at 0.5. And every subsequent term is going to be the same as the previous term, plus the slope, essentially, which is the derivative of dy dx, which is xy. So in this case, it's x of the n of the and yn, the previous x and y values for the previous terms, multiplied by the step size, which tells us how long, essentially in terms of x, how long each of these little line segments are. And now I just want to start working through this. So let's start with, x1's, to be honest, x is always going to be pretty easy. So if x naught is 1, then my first term is going to be 1 plus 0.5, so 1.5. My second term is going to be just that plus another 0.5. That's not really what we're focused on so much. That's just telling us I want to get to 2 there. It's the y part that really matters. And so we know that y1 is going to be the same as 0.5 plus x naught, which is 1, times y naught, which is 0.5, times the step size, which is 0.5. And if you can read my messy writing, we should get 0.75. And then y2 is going to be the previous term, which is 0.75, plus the previous x and y values, which is 1.5 for the x and 0.75 for the y, times the step size. And then we should get about exactly 1.3125, which tells us here that y of 2 is approximately, that's our approximation, 1.3125. I'll stick with all the values there. That doesn't mean that's actually what y2 is, that's our approximation. And again, the smaller our step size, the more accurate our approximation will be. Again, we have a couple of recursive equations here, and so here's one, here's another, which if we know how to use our GDC, like in the previous question, we can now save ourselves some time, and instead of doing this step by step. And so for part 2, I want to do the same thing. I want to estimate y of 1.5 and y of 2, this time with a smaller step size. So in this case, the main difference is we're going to have the exact same equations, but instead of adding 0.5 each time to x, we're going to have 0.1. And instead of multiplying each of our slopes here for y by 0.5, the step size will be shrunk down to 0.1, so we'll be multiplying by 0.1. Other than that, though, it's a matter of using your GDC. And if you are correct, we should get y of 1.5, or approximation, should be 0.881. That'll be 5 steps of the iteration, because each one is 0.5. I don't need to write it down, I said it out loud. And then y at 2, our approximation for this, should be about 1.93. And so while both this value here and this value here are approximations, we can feel more confident about this value since the step size was smaller. All right, so now we'll talk about a coupled system. A coupled system is a system of differential equations which are connected by some third variable, in general, time, and so seeing how things change over time. And so if you look at these two equations here for dy dx and dx dt and dy dt, they both have three variables actually, and t tends to represent time. In this case, though, they're just some equations. This is just to get a sense of how we work with this. So again, I want to use Euler's method with a step length of 0.1 to estimate the value when t equals 0.5 with all these many starting conditions. And so if I look here, this equation here, and this equation here, I want to now use Euler's method on both of these. And so x of n plus 1, this is what we're eventually going to put into our GDC, is going to be the same as the previous value of x plus the step size, so 0.1 this time, times the differential equation at that point, essentially the slope of the value at this point. And so if I look at for x, it's x plus y, so in this case xn plus yn times the sine of tn, the previous value for t. Or you could just leave it as t as well, because if we look at t, it's just going to go up. It's going to start at 0 anyways, but I'll stick with this. All right, and then yn plus 1, almost a very similar equation. It's going to be the same as the previous value for y, plus the step size times the slope of the differential equation at this point, which is very similar, xn plus yn, times the cosine of tn, the previous value for t. And we could create a third equation here. We could say tn plus 1 is just the previous tn value plus the step size. This time time is going up by 0.1 seconds, minutes, whatever it is. It doesn't actually say. And so what I can do now is I can create, while these are the most important parts here, I can create a system of 3 sequences. And depending on your GDC, you need to be aware of how to do that. But with each of these sequences, I also know the starting amounts. Notice t starts at 0, x starts at 3, y starts at 4. Those are like our t naught, x naught, y naught. And maybe let's write those down. So x naught equals 3, y naught equals 4, and t naught equals 0. And depending on your GDC, it should be fairly quick, because I want to estimate the value when t is 0.5 and each step is 0.1. That'll be 5 steps on our GDC. Helps if I can write. Sometimes I just can't. There we go, 5 steps later, ... And we should get when t equals 0.5, x is approximately 3.95, and y is approximately 8.21. And keep in mind again, these are approximations, and the smaller the step size, the more accurate our approximations is. The only way for this, essentially it's the limit as our step size approaches 0 that our approximation approaches the exact solution. Now, one common application of a coupled system is what we call a predator-prey system, where we have, in this case, wolves and deers, and the populations and the change in populations between each is affected by the change in population of the other, which makes sense if you think about how population of other predator or prey will affect one another. So we have this differential system here for W and D, wolves and deers, and we're given some initial conditions. There's 200 wolves at the beginning and 120 deer. And we want to use Euler's method with a step size of 0.5 to predict the population of these wolves and deers in 5 years. So it's essentially the same thing we did up here, with in some ways, no more complex equations. And it'll be a total of, in terms of steps, 0.5 years for 0.5 years to make it 5 years in the future. This will be 10 steps we have to do. Definitely want to use our GDC. What is with my writing this morning? Of course, that implies my writing is sometimes neat. So I'm going to look at function w wolves. So wn plus 1 is going to equal the previous population of wolves plus the step size, 0.5 years, times the slope, the gradient, whatever the differential equation for this, 0.0012 w, 12 w, previous value for w, so wn, times the previous value for deer, dn, minus 0.12 w again. And we know our initial population for wolves is 200. So for example, in the T84, that would be most likely my U sequence. That's how the T84 kind of usually by default starts with U. Then I have deer, so the n plus 1 is the previous population of deer plus the step size plus the slope for this function plus the the differential equation 0.1 dn minus 0.0005 wn dn with an initial population of deer equaling 120. If I want, I could create a third equation, which would just be for time, which again is somewhat, depends how you set up your sequences in your GDC, but it's not a bad idea and it's always quick. Tn plus 1 will equal the previous time plus the step size, and t naught equals 0. All right, that's it. Once you set up your GDC, we should fairly quickly get to see by the 10th step, and we should see when at t10, or when, I'll say when t equals 10, there are approximately 224 wolves. So W equals about 224, and there are approximately 117 deer. I actually don't need to say that. Keep in mind, just to make sure, I'll kind of show you some of the values that I see for my sequence here. So again, I'll write it like this: T naught, W naught, or maybe I'll say actually Tn, Wn, dn. So time 0, we should have what we're given, 200 and 120. Time 0.5, because we're going up in 0.5 steps. You should see in your GDC about 202.4 for wolves, and again, about 120 for deer, which means the change is so small, it's pretty insignificant so far. After T1, 1 year, we should see about 204.83 and 119.93. And then goes on, and eventually, like I said, the values I actually had was 224.18 and 116.75. That's what I had on my GDC, which again, I rounded to 3 significant figures, which makes sense for we're dealing with populations of animals here. So like I said, I'm not saying it's an easy lesson at all, but it is so much easier once we are familiar with a GDC. Once we have that down, it's fairly routine, but the technology speeds things up greatly.